Hello everyone. In the continuation of our lecture series on discrete mathematics, in the last class we talked about the concept of relation, what exactly a relation is, how we can visualize it, what are the different types of relation we are having. We take various examples along with some applications of the relation in CS and AIML domain. Now, in today's session, I am planning to discuss one another important type of relation, which is known as a partially ordered relation. Okay. Then, after partially ordered relation, I plan to discuss the concept of partially ordered set, and then we'll talk about the hash diagram, that a graphical representation of a poset. So these are the things I am planning to cover in this session. So let me share the screen. Okay, so let us talk about hash diagram, partially ordered set and hash diagram. So firstly, let us see poset. If remember, we talked about partially ordered relation in last class. So a relation on a set A or S is called partially ordered relation if the relation is reflexive, antisymmetric, and transitive. The relation is reflexive, antisymmetric, and transitive, then such relation we call as a partially ordered relation. Such a relation we called as a partially ordered relation. Now, just recalling what is reflexive relation, a relation is called reflexive relation if every element is related to itself. For every A from the set, A comma A belongs to R. What is transitive relation? A relation is called as a transitive relation if whenever your A comma B belongs to R, B comma C belongs to R, then A comma C must belongs to your R. So if this condition satisfies, we call this relation as transitive relation. At the same time, anti-symmetric relation, a relation we called as anti-symmetric if whenever A comma B belongs to R, B comma A belongs to R, then A and B must be the same element. Both of them are the conditional relation. If A comma B is in R, B comma A is in R, then A must equal to B. In the same manner, reflexive relation is what? Whatever A we are choosing from the set A comma A must belongs to R. This is what we call as a reflexive relation. These things we already discussed in the last session. So this is what a partially ordered relation. Now we are talking about a partially ordered set. So a set A along with a partially ordered relation R is called as a poset and denoted as like this. The first one is your set and the second one is the name of your relation. So a set along with a relation R which is partially ordered is called as a poset. Okay, any set with a relation which is partially ordered is called as a poset or partially ordered set. Now, whatever elements are there in S, they called as the elements of your posets. Now, let us take some examples on it. Set of natural numbers with the operation less than or equal to. If I am taking set of natural number and operation is less than equals to, that means our set over here is taken as 1, 2, 3, and so on. This is your set of natural number and the operation is less than equal to. So less than equals to means what? A comma B belongs to R if A is less than equals to B. This is how the relation is defined. Means what? 1 comma 2 belongs to R. Yes, because 1 is less than equals to 2. 1 comma 1 is there here because 1 is less than equals to b, and these kind of elements are there. Can I say 2 comma 1 belongs to R? No, because 2 is not less than equals to 1, so this element will not be there in your R. So this kind of elements are there in your relation. Now, so 2 1 will not be there in this relation due to it is not satisfying the condition. So this is what we are supposed to check. This is a poset or not. That means we are supposed to check a set of natural number with the operation R. Since operation is defined as like this, so we can write like this. We are supposed to check this is a poset or not. This is what the question is asking. So we'll say this is a poset if it satisfies three relation condition, which is the first one is a reflexive, the second one is anti-symmetric, and the third one is transitive. So we can say the relation R is reflexive. Why it is reflexive? We can say R is reflexive. Why? Because whatever A you can choose, A comma A will always there in your R. Because every number is less than equal to itself. 1 is less than equal to 1. 2 is less than equals to 2. 3 is less than equals to 3. So for every A from natural number, A comma A is there in your R. Hence, the relation is reflexive. So the first condition satisfied. Second condition is anti-symmetric. So what anti-symmetric condition is? It says that if A comma B belongs to R, B comma A belongs to R, then A must equal to B. Anti-symmetric relation. So now just take the example. Do remember it is a conditional statement. So first we are supposed to make if condition true. So if A is less than equals to B and B is less than equals to A. Now try to assume some AB where first element is less than equal to second and second is less than equal to first. It is only possible when both of the elements are same. Like if I'm taking 1 comma 2, so 1 comma 2 belongs to R, but 2 comma 1 not belongs to R. So this pair can't be taken 1 2 with 2 1. So the thing is that if condition will only be matched when A equal to B, or just try to assume, try to visualize the thing. A is less than equal to B. B is less than equals to A. It is only possible when both the elements are same. Hence, the relation is anti-symmetric. The third one is transitive. So transitive says that if A comma B belongs to R, B comma A belongs to R, then A comma C must belongs to R. Now, in the context of relation R defined over here, A is less than equals to B, B is less than equals to C, then A must less than equals to C. Yes. So whenever A is less than equal to B, B is less than equal to C, A is also less than equal to C. Hence, the relation is also transitive. Since this relation R satisfy all the three relation conditions, reflexive, antisymmetric, and transitive, hence we will say this relation or this is a partially ordered set. The relation is partially ordered relation and hence natural number with the operation less than equal to is a partially ordered set or poset. This is how we write if a condition is true. For every A comma A belongs to R. For reflexive in the same manner for other relations too. Taking second example, set of positive integer with the relation divisibility. Now, divisibility, as we already discussed, divisibility means what? The relation is defined such that A comma B belongs to R if A divides B. If A divides B, this is how the relation is defined over here. And divide means we are talking about complete divisibility. This is how it can be written mathematically also. So they are saying A comma B belongs to R if A divides B. Is this relation is partially ordered relation? If this relation is partially ordered relation, or we are supposed to check set of positive integer with the operation divisibility is poset or not. This is how it is written. Okay. So let us do check it. Divisibility is reflexive. Yes, it is reflexive. Why? Because every a comma a, for every a comma a belongs to R. The reason is what? The reason is every number divides itself. 1 divides 1, 2 divides 2, 100 divides 100. So, satisfying the condition, hence, this relation of divisibility is reflexive. Is this relation is transitive? Yes, it is transitive. If A divides B, B divides C, then A also divides C. Like 2 divides 4, 4 divides 100, 2 divides 100? Yes. So, if condition formulated and then condition satisfy, so the relation is also transitive. Talking about anti-symmetric. So as anti-symmetric, what it says that a relation is said to be anti-symmetric whenever A comma B is in R and B comma A is in R. Then A must equal to B. In the context of divisibility operation, if A divides B and B divides A, then A will always equals to B. If you are taking two different A and B, let us take 4 and 8. So 4 divide 8. So 4 comma 8 belongs to R, but 8 does not divide 4. So we can't take this pair. So pair is such that A divides B and B divides A. And this condition will only formulated when both A and B are same integer. So yes, the operation divisibility is anti-symmetric too. Hence, all the three conditions, which is reflexive, anti-symmetric, and transitivity hold. So this relation is partially ordered relation, the divisibility, and this complete set is poset or partially ordered set. One more example, the power set with subset relation. Now, in this example, we are supposed to check power set, and the relation is what subset. That means which kind of elements will be there? A comma B belongs to R if A is the subset of B. A is the subset of B. What is power set? Power set is the collection of all the subsets of a set A. Collection of all subsets of a set A. So you can take power set and think on subset operation. So subset means what? A comma B belongs to R if A is a subset of B. A is said to be subset of B if every element of A is in B. The definition of subset. Okay, is this relation is reflexive? Yes, because every set is a subset of itself. Every set is a subset of itself, so the relation is reflexive. Yes. Is the relation is transitive? Let us check. If A is the subset of B, B is the subset of C, then A also having subset, A is also subset of C. All the elements of A is in B. All the elements of B is in C. So it's quite common that every element of A is in C also. So A is also subset of C. Talking about anti-symmetric, if A is a subset of B and B is a subset of A, then A and B must be the same set. If A is a subset of B, B is a subset of A, then A and B must be the same set. Hence, the power set of A or any sub collection of subset we can say with the operation subset is partially ordered set, or we can say poset. So this is how we can understand Poset with the help of these three examples. Let us take one more example. Now consider R as a relation on set of peoples such that X comma Y or X is related to Y. If X and Y are the people and X is older than Y, show that R is not partially ordered. What they are saying? They are saying that X comma Y belongs to R if X is older than Y. If X is older than Y. Older means we are talking about age. If age of A is more than age of B, then A comma B belongs to R. Is this relation is partially ordered? The answer is no. Why no? Because it is not reflexive. Why not reflexive? Because X comma X does not belongs to R. Now try to understand what we means X comma X. So as per the rule, if X comma X belongs to R, it means what we are saying, X is older than X. We are saying that X is older than X, which is not logically correct. Myself can't be older than myself. Okay. If it is like equal or older, then it may work. But older means what? It will not work. So X comma X does not belongs to R. X comma X does not belongs to R. So the relation is not reflexive. Now there is no need to check other things because in order to be a partially ordered relation, it must reflexive, anti-symmetric, and transitive. It is not reflexive, so not partially ordered. Even we can think on others also. Like, is it transitive? So the answer is yes. Whenever x comma y belongs to R, y comma z belongs to R, we can say x comma z also belongs to R. X comma z also belongs to R. Like here, x is older than y and y is older than z. So x is also older than z. Yes. So it is transitive. In the same manner, we can check for other things like antisymmetric or other relation. So this relation finally not reflexive. Due to not reflexive, it is not partially ordered relation. Moving ahead, there are few more examples to check whether these relations are partially ordered or not. So the first one is what? We are taking the set is set of integers. It's not given positive or negative, only integers. And R is a relation defined as this. So first one is what? X comma Y belongs to R if and only if X is not equal to Y. If X is not equal to Y, then they comes in your R. For example, 1 comma 2 will be there in your R because 1 and 2 are not equal. 1 comma 1 does not belongs to R because they are equal to each other. Understand? So the pair where first element is not equal to the second one, where the first element is not equal to the second one, will be there in your R. Is this relation partially ordered? The answer is no. Why no? Because it is not reflexive. Because 1 comma 1 does not belongs to R and 1 is an integer, na? Reflexive relation. For every A from the set, A comma A must be there in your R. And I have one counter example, 1 1 is not there, so not reflexive. This relation is not reflexive. Not reflexive means what? This is not partially ordered. This is not partially ordered. So now there's no need to check other, even though if you want, you can check it. Second one, x equal to y plus 1. It is also not reflexive. It is also not reflexive because 1 comma 1 will not be there. 2 comma 2 will not be there. The third one, if and only if x dot y is greater or equal to 1. Is this relation is partially ordered? The answer is no. Why no? Because it is not reflexive. Why not reflexive? Because it is on set of integer. Okay, we are supposed to think on it. It is greater equal to. If it is greater than, then it is not. If it is greater than, then 1 comma 1 does not belongs to R. If the relation is x dot y is greater than 1. Because 1 dot 1 is not greater than 1, na? So not reflexive. But it is greater or equal to. So now we are supposed to think on, is it reflexive? Is it reflexive? I think yes. 1 comma 1 is there, 2 comma 2 is there, minus 1 comma minus 1 is there, minus 2 comma minus 2 is there. For every A comma A belongs to R, so the relation is reflexive, yes. Now let us talk about the anti-symmetric. So 2 comma 3 belongs to R, yes. 3 comma 2 belongs to R, yes. Because you can see their product is greater than 1. 2 dot 3 is 6, which is greater equal to 1. 3 dot 2 is greater equal to 1. So yes, they are satisfying the condition. So what anti-symmetric relation is saying? Whenever AB in R, BA in R, then A must equal to B. 2, 3 in R, 3, 2 in R, that means we must say 2 equal to 3. Can I say 2 equals to 3? No, they are two different integers. They can't be equal. So this is not anti-symmetric. This is not anti-symmetric. You can see if condition satisfied, but then condition failed. And it is a conditional statement. And in conditional statement, I always told you, if condition satisfy, in that case, then condition must be satisfied. Okay, so this is how we can say this relation is also not partially ordered relation. We can check it for transitive also, even though it's not needed for partially ordered relation. Okay, so this is how we can understand what is a partially ordered relation and what is a partially ordered set. Okay, students, so that's all for this session. In the next session, we'll talk about the hash diagram of a partially ordered set, or we can say the graphically representation of a poset. Now closing the session.